Okay, I don't think some of your monitors are working, so you'll just have to watch up here. I'm not sure how to fix that. It looked like only 6 or 7 were on. But we'll just move on. Today, here's the attendance. Today we're going to do 19 and 20. Monday we'll do 21. Then Wednesday we have our field trip. And there's also a take-home test next week. So with that, let's quickly go over these 2 chapters. Cladding systems is basically that's the exterior skin of a building, like a rain screen, something to keep the water out. It's not the structure. It's the windows or the stone that's basically hung on a framework. Like it says here, you got to keep the water out, and you got to detail it so it won't leak. And we'll do some detailing on that later after we're through looking at the slides. And air leakage, you know, you don't want the cold or the hot air going in or out. You want to keep it where it is. Primary functions, another function is controlling light. If you have a glass system, of course, you'll want to have it tinted so that you aren't just baking inside the building. And controlling the radiation of heat with films on your glass. If you have stone, that's not quite so much a problem, but you need to be aware of what your cladding, which is the exterior skin of the building, will do. Here you can see a slide showing brick over an insulation system. So that's going to be like a cavity wall. Also, you need to control sound. You don't want to be sitting in your office hearing the sirens below and all the stuff going on. So you need to, all of these elements are can be specified in whatever system you use. You know, we've studied that through the semester. Sound is controlled by an STC rating. So you just look for those properties when you're choosing your material. Just another picture, different type of system. Wind forces, it's got to be able to stay in its framework and withstand the wind, and that's just and the wind pressure gets higher as the building gets taller. So the very tall skyscrapers obviously have to take that into heavy consideration so that their panels don't pop out of the framework. Controlling water vapor, you don't want the moisture, you know, even if it's not raining, humidity, whatever, can seep through. So you want to be able to keep that out, as well as the rain, because the moisture is what is the chief cause of decay for your finishes. Secondary functions would be movement, expansion and contraction, moisture, expansion and contraction. And this just kind of is a little diagram showing you know, the cold air and the hot air and how the building might move with those issues. Structural movement. Way back in the beginning, we talked about how the foundations can move, and of course that will affect the whole building above. So you need to allow for some of that naturally, but then, you know, you want to make sure that, I don't think you'd want it this drastic, but columns will tend to shorten. Beams will tend to deflect, meaning they'll bend down. Wind and earthquake, you know, if there is a windstorm or an earthquake, you don't want the building to collapse. Even though it might be damaged, it can still stand up until the people get out. Spandrel beam deflection. Differential foundation settlement, that was, you know, when the foundation moves, and differential spandrel beam deflection. So all of those different things go into a successful cladding design. It's got to resist fire, of course, weather gracefully. This one doesn't look like it's weathering very gracefully. You want your materials to be able to be cleaned or not attract dirt necessarily. When it rains, you want it to wash off easily. You don't want it to oxidize or grow moss on it, stuff like that. Bless you. Here's installation requirements. That's always an important factor. Typically, you want to be able to install it from the inside. That's a little safer than installing it from the outside, hanging off scaffolding. So you can see that and we'll watch a little video, I think, in a minute of them lifting this stuff up, and then even they're still wearing their safety harnesses because it's precarious leaning over, but it's a lot easier to do it if you're standing on the inside of the building versus hanging on the outside. So this is important for an architect to know. How do you get it to be watertight? And this just shows the way water moves. I think we talked about a little bit about that earlier. You've got your sealants and stuff, but it can still creep in there with the pressure. If you got a positive pressure on the outside and a negative pressure on the inside, that will tend to suck that water through there. So you really need to design it correctly and seal it and flash it and all that stuff to keep that water out. Even if it seems like a calm day, there's still going to be air pressure differences, especially the higher up you go. Gravity forces, you don't, if this is the outside of your building right here, you don't slope the joint toward the inside. That's kind of obvious, because what will the water do? It'll just run right in there. So instead you slope it this way, because it'll be harder for that water to run uphill. It'll just keep on the outside. Momentum, like if it's a driving rain, if this is just squared off, the drops will come in and bounce in. But if you have it a zigzag approach like this, they'll get in there a little bit, but then most likely most of it will come back out. The labyrinth, that's what they call that. Surface tension, if you just have a flat thing, the water will tend to seep right along, keep along the surface until it gets to where it won't go up, it'll just fall down and go back in there. But if you provide this little drip, that's a very important detail on windows, on cladding, on everything. The water comes along and it won't go up, so it'll drop down there and then fall back to the outside. Capillary action is another one where it will pulls the water through any opening. The force can be dealt with by making openings in walls wider than a water drop, or by providing capillary breaks by providing a coating of silicone-based water repellent. So here, this opening, or there is no opening there, and here they've provided this little gap that stops the capillary action. Air pressure, like we talked about a minute ago, that can drive the water in, and so to prevent that, you usually, if you have a big gap like that, you'll have a pressure equalization chamber, and that is where the water will, this is sealed off from the inside, so in essence this pressure is the same as this pressure, so the water won't be sucked in, it'll just keep going down. Rain screen cladding and pressure equalized wall design. This allows the wind pressure differences to neutralize. You got the wind coming in, outside, inside. There's a little pressure chamber in there. It's called the PEC. Whenever you see that, it's called a pressure equalization chamber. This is just an example. Y'all can study these, on your own and look at these closer. I think they're also in the book. So this is we're going to actually do this detail in a little while, and I'll let you go back to this slide and look at it. But this is on a smaller scale, like on a house. You still have to have the same components. to keep the water out. So the weather strip acts as an air barrier. That's right there, that little piece of material. And then that one right there also keeps the air from going in and out. The wash or the slope on the sill facilitates the water to go downhill toward the outside. The groove in the lower edge acts as a drip to counteract the surface tension. And the L-shaped joint between the sash and the sill acts as a labyrinth, this right here, so water won't go up. So this small window has all the same components that a large commercial structure would have. And you need to be able to identify those components in your design. This says this side is incorrect. It's better to have the weather stripping actually on the inside edge, because this will just get, the reason that's incorrect is because that will get wet and deteriorate. So then there's sealants, like caulk. All y'all are familiar with caulking. This is, there's gunnable sealants. There's 3 different categories, and you know, when you start detailing this kind of stuff, you have to be familiar with it, understand low-range caulks are to fill minor cracks. Medium range, such as butyl rubber or acrylics, are used for sealing non-working joints, meaning they'll stay stiff. The high range, such as polysulfides, polyurethanes, and silicones, are highly resilient and durable for 20 years or more and used for working joints. That means they give and take. They'll bend back and forth. Sealants and gaskets are a solid type of sealant. Strips of cured elastomeric membrane compressed into a joint or installed into a lock strip insert right here. Preformed cellular tapes are another kind, and preformed solid tapes. Shows you different examples of the gasket type material, sealants. When you put caulk in a joint, there's a right and a wrong way to do it. And you have to tool. You can't just like squeeze it in there and leave it there. It's important to tool the joint. The width is to control the strain. The depth is to control the stress. Correct proportioning to control the strain and the stress. It talks about the typical installation steps. Apply a primer. The backer rod, which is this circle thing. Sealant is extruded into the joint. So here you can see that this one's untooled and this one's tooled. If it's too narrow, here it's too wide, obviously. Here it's too deep. Here the bead is correctly proportioned on that one. On a lap joint, here it is correctly proportioned. You don't want a gap between them. You want it to obviously seal it. Here you also need a bond breaker. Sealant should only contact 2 sides of the joint. If it contacts the 3rd side, then the effective width of the sealant is reduced, resulting in strain. So you have to add this bond breaker so it doesn't actually stick to this side right here. You also have to be knowing about the temperature that it's going to be at and how it's going to react in cold and hot temperatures, and make sure it is designed and applied to withstand whatever it's going to face temperature-wise. So cladding systems, I think we talked about a curtain wall earlier, but if not, we will be. Until the late 19th century, most skyscrapers were built with load-bearing walls, meaning they were just masonry or brick or concrete all the way up. And now, of course, it's mostly steel construction, and then you have the framework on the outside of your building to hold up the curtain wall or the cladding system. And this was relatively new in the 19th century, and then came in. It's pretty much all we do right now. So even if a building has stone on the outside, it's really only about 1 inch thick. It's held held up by a framing system. Of course, everything has to go through testing and all that stuff. They'll build mock-ups of the system, and then they'll test it, and then you know, it'll be determined whether it's acceptable or not. The building codes are looking for things about structure, fire, and energy, and it has to meet all those standards. And there's so many different materials out there, it's impossible to teach you about all of them. It's just once you get into designing, you have to be able to understand what you're looking for, and then look at those. Make sure your system is going to apply there. See if this movie works. I think this is the one where they're, yeah, this is like a ballet, but it shows you how they put it up, I think. It's not really a ballet, but it has ballet music. How they do that in real life. So this, now we're moving into chapter 20, cladding with masonry and concrete. So just like you can clad with glass and steel panels, you can also do it with masonry and concrete. You can have pre-manufactured masonry veneer curtain walls. Typically you'll have your structure, you know, your columns and your concrete and steel behind, and then you'll have a shelf angle that the brick sits on, and then they just do it, you know, story by story. Talks about the flashing. That's very important to make sure if any water does get back there, it won't touch the structure and it'll roll back out. This backup wall of concrete or steel studs is shown back here. You can see that. And here's a detail. This would be a great detail for somebody to study and copy. You know, all y'all have to do is go back. I put all these slideshows online so you can stare at these and copy them. But if you look, this is obviously a concrete masonry wall. It has the insulation, the air gap, the brick, the concrete structure, the shelf angle that the brick sits on every now and then, the ties. I mean, you can study that, but this is basically a slice through a wall looking sideways at how the wall is put together. You still need to have the vertical joints for expansion and contraction when you do this, because it will, the building will move and you'll need to have room for that. Here's another good detail to look at. You know, this is a typical detail of what this wall might look like with a steel construction, steel studs, a brick veneer on the outside. Notice that the brick is slanted at the window to let the water go down. You can prefabricate the panels. Here's a row of them in a factory, and then bring them out to the sites and put them up similar like they just did that glass on the last video. Here you can see them putting in a corner piece and a straight piece right there. Stone works a similar way as glass. I mean, you got your panels or your framework here, and then you insert it into the panels. It clips on. You can see there's a close-up right there. The stone is not structural. The structure is behind it, being the concrete columns in this case. You can see right there. Here's a picture of what that looks like in reality. You have to have your weather-resistive membrane on the behind that stonework. This too means that they've shown those black lines indicate where the studs are behind that membrane, so that they can actually screw these into some structure and not just into thin air. Very important. Here's a close-up. You can see the clips that the stone that anchors the stone inside. There's another good detail. showing how stone would be on a metal frame building. This squiggly stuff around the beams, that's the fireproofing. Remember we talked about having to fireproof things because you don't want this to melt and fall down before all the people get out. This is the roof section, and this is a typical floor section. This is where the wall meets the roof, and this is floor. Here you can see them putting those up, similar to what we just saw in the video. Just some more details of how limestone might work. If you have if stone is very, you want it to be thin so it's lightweight, you can stiffen it with backing of different materials. Here they're talking about metal honeycomb mounted on the spandrel panels, or thin sheets can be put on precast concrete. I think we'll see that in a second. Precast concrete is very economical because you, of course, can do it in the factory, and you can add all kinds of special finishes to it where it looks like stone, where it looks like brick, but it's a lot cheaper and more economical to do. And they're just talking about how they make different finishes here. Here's a ribbed finish with this machine. You can put the little rocks on it too. Here's another detail of a precast concrete panel system. You got your floor and your beam, and then you got your clips that hold the panels on. 3 indicates there would be an interior wall, stud and sheetrock here, but they're not showing that to keep the detail simple. Here's what that building would look like in reality. Here's a good side view of what your section might. You got your concrete panel, you got your insulation back there, and your safing, which is also a fire insulation. That would be this right here. They squirt that in there to keep any smoke. What that does is, because if there was a fire on the floor below, if there's any pockets or air pockets, the smoke could just come up and get into the floor above. So you seal it off with safing, that foamy stuff you squirt in there, and it seals up all the openings. When you have to have a fire separation, you have to do that. Here's the glass fiber reinforced curtain walls. There's another type that you could do. Advantage of that is it can be molded into unusual shapes. Here's a detail of that. There's probably like 20, 30 points of details in this slideshow for those that need it. Here's how you would treat joints. They're talking about the backer rod and the joint and how big it has to be, the sloping, etc. These are things you need to look at and study so you understand. EIFS is exterior insulation and finish systems. That's gotten a bad name in the past because it's basically a prefab stucco panel, but if you don't install it right, it can get all moldy and gross looking. Typically commercial buildings, they have good installers that are they've been trained in this, but if you put it on a house, a lot of times, if you're trying to save money, but the contractor doesn't really have people trained in that specialty, so there's a lot of issues when they put it on house. The house across from me looks like a mold farm because it has EIFS all over it. But I think in commercial applications it works good because usually you have the right kind of people installing it and knowing what to do. This is a picture of it. You got a stucco finish on like a styrofoam and then a backup. This is all one panel. And if you don't drain it properly, if you don't let air get into there, then it'll just be a mold factory. So rain screen, most masonry and concrete cladding systems except brick veneer are barrier systems, meaning they keep, you know, most of the rain out, most of the wind out. Cavities behind these systems are interrupted by framing and attachment components. They have been isolated efforts to design true rain screen details for stone and concrete cladding systems, but more research is needed. Because of they're talking about these clips and the support, you know, somewhere that's the rain is gonna get, you know, hit that and not have a way out. So you've got to just be really careful when you're doing these that you flash it and detail it correctly so that most of the rain can get out. Here we have masonry is found in these sections of the specifications and concrete cladding. And that's the end of that. Okay. Oops. I want to go back to that detail. There it is. Why isn't it showing that? Let me get it this way. Okay. I think we actually have 2 sheets to do. I'm going to help y'all, so have no fear.
You.
So on this one it says, in the 2 assemblies below, identify all elements related to keeping the water out of the assembly. Label them according to their rain screen design functions, including rain screen, pressure equalization chamber, air barrier, etc. So it's not exactly the same detail as this, but let me see a second. What's the best way to do this? I think actually I'm going to do this. So on the first one, hold on one second. Let me see if I can pull this up. I can't get it any bigger though, but okay, it says, so you have your door right here. It shows you your weather stripping. It shows you your aluminum drip, which is important. And it shows you your wood sill. So what you want to do, like it says, is identify the elements related to keeping water out of the assembly and label them according to their rain screen design function. So what elements here do you think are keeping the rain out, first of all? The what?
That groove on the bottom left.
This? Okay, what is that doing? What design function according to rain screen is that doing? Well, how's that keeping the water out?
That way instead of creeping up inside.
Okay, well you got the drip, which is actually like a rain screen. Let me see. Find my little pin. So what you would do is label this on your sheet, you know, point a little arrow there. I can't write as little as this is, so it's going to be bigger. But so that's a rain screen because it's keeping rain out. But then what is there's more here. What's this little thing right here is a rain screen. But what do you think this is in here? That little space. What was that? Pressure, right. The pressure equalization chamber, and I'll just call it PEC. So that's going to equalize the pressure between the outside and the inside. So you need to write that on there. There's one more element. Of course, there's several here, but what do you think? Do you see something else that's helping with the rain screen? Hmm? The what? Speak louder. The slope? What did someone say? This right here? Right, because it's sloped downward. So that's, you can write slope. There's something else keeping rain out and air out. We got a door, we got weather strip, we got aluminum drip, we got a wood sill, and we got a door sill. Well, that's the title of it. Something else you haven't noticed yet. It's written on there. Look on the inside. Weather strip. What's that doing? Water and what? But it also does something else. It provides, what does it keep from getting in there? Like on a cold day, you would have a weather strip to keep something out. The wind or the air. So that's an air barrier. I think that's pretty much it for that one. Let me see if I can get the other one up there. Fine. Let me select. I'm just going to do it this way. Copy image. Over here. That sure makes it small, doesn't it? It's not going to be very clear, but as we can kind of see it. Okay, so for this masonry cavity wall section, what's the primary thing keeping the rain out? What element? You've got a masonry, you've got a cavity, you've got a pressure backup wall, you've got flashing and weep holes, but what's the first thing keeping that rain out? What's the rain going to hit first? Masonry. So your masonry is your rain screen. Whoa. So you'll label that rain screen. Okay, then what's something else that they've labeled here? Like, what is that cavity doing? What is the air pocket between the brick and the, what rain screen function is that performing?
PEC.
PEC, that's right. So your cavity is your PEC, pressure equalization chamber. And it's also actually doing another job, which is kind of the same, I think, but it's air barrier, that's right. So you could label that also air barrier. Then, what else in here is performing some sort of rain screen function? The flashing, that's right. And it's hard to see here, but you can see it easier on your sheet. It keeps the water, because it's heading downhill, it provides a labyrinth. I don't know how to spell that, but okay. So that's pretty much it on that one. Those are just being able to identify and design those elements into your wall is an important thing. Now I'm going to give you another sheet that we're going to work on. This has to do with chapter 20. Has everybody got that? The first one? Let me see if I can get a picture of this one up there. Masonry cladding. Oh, it won't let me be part of it. Oh, that's the same one. Dang it. Edit. Select all, edit, take a snapshot. Why isn't it doing my new one? Maybe I got to copy, edit, select all, edit, copy, edit, paste. There we go. Okay, so this one asks you, in preparation for this exercise, review chapters 19 and 20 of the text, paying particular attention to pages 810 through 817 and the related figures. To the exterior wall section below, add and label all components needed to make a watertight wall with 1 inch of insulation in the cavity. First, let's look at these pages, page 810 through 817. Okay, it shows you all the components in, detail. And here's this is kind of what we're going to look at, this picture right here, everybody.
What page is it?
813. For this exercise, we're not concerned with everything. What we're concerned with is what makes this a watertight wall. So we don't really care about the fireproofing and all of this stuff over here. But which of these elements are going to make this a watertight wall? And we need to label them and fill them in there. So, so first of all, it says you're going to have a 1 inch of insulation in the cavity. That doesn't appear to be drawn there, right? But it's in this detail on page 813. So the first thing, we need to consider that, but then before we actually draw that, there's something missing right here that would interrupt that insulation, and that would be the shelf angle that's on that picture. So I can't draw it very well on this scale, but y'all need to try to copy that picture and draw that shelf angle kind of like that, because that's what that brick sits on. Then on top of that, well, the angle will have some sort of connection into that beam, but then you're going to draw your 1 inch thick insulation, you know, as straight as you can, above and below that. And you'll hatch it in little squares like they did. I'm not going to do that here. And you'll label that 1 inch insulation. And you still, if you draw it right, you'll still have a pocket of air, right? So that's going to be your air cavity, or your PEC. They're calling for, this wall in the book is shows 2 inch insulation in a 2 inch cavity, but they specifically told us 1 inch. So, we'll use the air cavity as 2 inches.
You had that acre there?
The what?
Right there by the.
Show me in your book.
You have that little square right there. On that shelf angle.
Yeah, that's just a bolt going into the. I can't draw it very well on here. So above, actually, what's going to be on top of this shelf angle? Does it show it there? Shelf angle. Oh, yeah, it does. If you look up here, it says continuous flashing. So you can, I'll draw that in a different color so you can kind of see it. But your flashing is going to go on top of this shelf angle, all the way up behind this insulation actually, and into there. So that will be your flashing. Continuous flashing, however you spell that. And you can see that it's a darker line in the detail. Then over here, another thing that's going to keep the water out is the, again, it's hard for me to draw, but you're going to have your backer rod under the angle and some sealant right there. So you just kind of need to draw that like they've drawn it in your book. They got the, you know, blown up. It looks like you got a circle, and then you've got some sealant. So you need to draw that right there and label it. Y'all see anything else that would be important to label pertaining to rain screen design? No? What? 2 bars at the bottom. On your book? Let me see what you're talking about. Yeah, we can label those. It's, that's actually the masonry ties. And you can see if you look at those, they're every now and then, they're labeled up at the, you have them like every so many bricks. And it would be where the joints actually line up with these joints. So, like right there, right there. So you could label those if you want. And what that does is binds the masonry to the backup wall. It's just a little piece of metal that's embedded in the mortar in both places, and those. And that will keep the, this wall from going out like that. So, masonry ties. It shows it in the book. Let's see. I thought I saw it a minute ago. Well, the plastic clips are part of it, but it's also called, it should be called masonry ties. That's what I call it. Oh, ties in dovetail slots. Just call it masonry ties. So we got our insulation, which keeps the cold or the hot air out. We have our air barrier, which acts as a PEC and also acts as insulation. We have our continuous flashing shown right here. So if any water gets back there, it's going to head out. We got our backer rod and sealant, which keeps the water from getting back into there. We have masonry ties. So that's pretty much it as far as waterproofing goes for that one. So, that's all I have, unless y'all want to ask me more questions on the review. I'll do that for this chapter. If you know everything, you can leave. But hand me these so I can give you credit once you're done. I'll be putting the map and the information for the field trip on Canvas, and then I'll also hand it in on or hand it out on Monday. But you need to be thinking, if any of y'all want to ride out there together and carpool. I can't take anybody, that's against the school policy. But it'll take you about 30 minutes to get there, and you need to be there at 9.
Next week?
A week from today.
Where are we going again?
It's going to be out on the island. I'm going to put the exact address on Canvas and draw a map.
On Wednesday?
Uh-huh.